Welcome. We are covering linear programming, and we were looking at what we called hyperplane separation theorems. In pictures, the hyperplane separation theorem was, you were given some two convex bodies, and if they were non-intersecting, then we, in some sense, either weak sense or strict sense, we could always draw a hyperplane between them. That was the hyperplane separation theorem, right? Specifically, one thing we did was, if there is a point outside a convex body, then there is a strict separation with a hyperplane, right? And we said that there are many versions of this hyperplane separation theorem, depending upon what kind of convex bodies we are considering, whether the separation is strict or not strict. One of the separation which is very useful is Farkas lemma, which talks about a cone and a point outside the cone. Okay. What it mentions is that given a point outside a cone, there always exists a hyperplane passing through the origin, which distinguishes between the cone. There are two ways in which it is different, right? One is, we have a special convex body, which is a finitely generated cone or a convex cone. The other thing is that the separation is not strict. In this case, one of the point of the cone will lie on the hyperplane, but the hyperplane is passing through the origin. Okay, so the B, when we write for the hyperplane A transpose X less than equal to B, this B is 0. Okay. I will do a different proof of Farkas lemma, but actually it can be obtained from this theorem. Can you give me an intuitive reason why, if you have a convex cone, you have a point outside, why should there be a hyperplane passing through the origin which separates the two? So remember, what will this give us? It will give us a hyperplane with strict separation, but it might not pass through the origin. So given a hyperplane from this theorem, which is a strict separation but which is not at origin, how do you convert it into a separation with a hyperplane which is at origin? By how much? What is theta? Okay. Okay, hint. The answer is very simple. Suppose for a cone, you are given this equation. Okay. A transpose X less than equal to B. Do you think this B matters? What is the definition of cone? Suppose there is a convex cone for which you have this equation A transpose X less than, I say that for all X element of cone, A transpose X is less than equal to 2. My claim is for all X, A transpose X less than equal to 1. A transpose X less than equal to 0.5. A transpose X, whatever you want. Why? What do we know about cone? The equation formed of the 0, but here I think it's a clear, simpler reason, which is from the basic definition of cone, right? Suppose, okay, A transpose X is less than equal to 2, but there exists a particular X naught such that A transpose X is less than 0.00000. Then what do I know about X naught? Huh? What can I create a new point such that A transpose X is less than equal to more than 2?
We can, because it's a cone, right? Alpha greater than equal to 0, so we can multiply it.
Right. You can multiply X naught with whatever damn constant you want. Multiply it by 1 million, multiply it by 1 billion, whatever you want. Right? So then that means there exists, so this implies there exists Y such that element of the cone such that A transpose Y is, sorry, this was equal to 0.001, this is greater than 2. So if in cone there is anything which is positive, I can attain any positive number. If it attains any negative number, then I can attain the entire negative real line, right? So for a cone, this does not matter. So what you are going to do, and it is given as an exercise for you, suppose according to this lemma, this theorem between a point and a convex region, suppose this gives you some hyperplane which separates this point and this convex cone. Just make B equal to 0. That's all. That means you just shift it to origin. That is going to be your separating hyperplane. It's as simple as that. And that you can convince yourself pictorially, but definitely should do it by equations. Sounds good? So look at the one, the hyperplane is given by this theorem. All the elements in the cone will have the same sign. The entire either negative real line or the positive real line. This is going to have opposite sign, obviously. Right? It's a separation theorem, so that you can do it. Right? Okay, great. So we know one proof of it. Let's do another proof of it, and which probably comes out more naturally if we look at a Farkas lemma in a slightly different way. Okay, so what does Farkas lemma say? Suppose we are given points x1, x2 up to xk, right? So these are some columns. These are going to be something for which we are going to make linear combinations of, and you can think of this as a matrix C or a cone so what are you doing? You are just putting all these things in as columns. So you can make a matrix out of it. I am calling that as C. Okay. Now, what is the cone? It's any positive combination of these things. Okay. So C multiplied by a vector which is entry-wise positive. Okay. Okay. And then you are given a point in the possibly in the range. Sorry. N. So exactly one of the two conditions are satisfied. Either there exists a linear combination of these things, that means B is in the cone, right? This is saying, this line is saying B is inside the cone. Or okay, let's make meaning out of it, right? Does this look like a hyperplane separation theorem? What is the hyperplane here? A transpose X equal to 0. That's the hyperplane here, right? So if this is the case, exactly one of them hold. Right? This is your hyperplane separation. Either the convex bodies intersect or you have a hyperplane separating them. This is exactly the same statement. Either B is inside the cone, they are intersecting, or there is a hyperplane. What is the hyperplane? A transpose X equal to 0. But why does this say that hyperplane separates with the cone and the point? What does this mean? So notice what this is saying. This is saying, this is same as saying right. So this is the vector inequality. What is the first coordinate of it? A transpose x1, second A transpose x2, and so on. So you are saying that the inner product of x1, x2, xk with all a's is negative. So now if you take even a linear combination with positive things, the inner product is going to be negative. So that means, so for all alpha, this is going to be positive. Okay. So even though this might look like a bunch of equations, this is a hyperplane separation theorem staring at you. Questions? Sounds good. Sorry, alpha? Rk. These are the coefficients of x1 to xk. K is the number of vectors, n is the dimension of the space in which they reside. So which one do you want to be k plus 1? This alpha 1 to alpha k? Yeah, alpha 1 to alpha k are constants. So k of them I can think of them as a vector in R to the k. That's why I have just written alpha. It's just a shorthand. Yeah, this is same as saying each of them are element of R plus. Yeah. Just wanted to be lazy. Okay. Sounds good? So now we know this is a hyperplane separation theorem between a cone and a point. Let's prove it. Which direction is easy? So what you want to show is both of them can't hold together. If this doesn't hold, then this holds. Exactly. How do you prove that two things? Exactly one of them holds. Both of them can't hold simultaneously. If this holds, then this. If this doesn't hold, then this holds. Which is the easy direction. And I'm not going to answer it. I think you need to wake up from your afternoon slumber. Tell me the answer. This is not hard at all. Notice that. This is where the answer is hidden. Sorry? If first holds, then second can't hold. Or other way to say it, both can't hold simultaneously. That's very easy. So now Arpit has helped you. What is the proof? Others. Why can I clearly say that if the first holds, then second can't hold? If B is equal to C alpha, that means B can be written like alpha 1 x1 plus alpha 2 x2 plus alpha k xk. Now, if A transpose C is less than equal to 0, then A transpose B has to be less than equal to 0 by the same thing. Okay? So let me just write the simple idea. Both can't hold. If one holds, implies there exists an alpha such that that would imply A transpose B is less than equal to 0. Right? And why did you take so much time? Think about it. Don't think about it, this is an equation. What you are saying is that if there is a point inside the cone, then there cannot be a hyperplane separating them. Should that be hard? Right? This is what you have proved by equations. So that's why I am saying this geometric intuition and the mathematical intuition. Just think of it back and forth and you will realize that you were like being in tension without any reason. Right? Where there is no stress, you are creating stress. Okay? But now is the question of creating stress. This is the hard part. So now I want to show that if one does not hold, then I need to search for A. Sorry, that is my mistake. And this will require this old theorem which we had seen 3 classes before, 2 classes before. We know cone in multiple ways. So finitely generated cone can be thought of as positive combinations of x1, x2, xk, or remember we had equivalence between polyhedras and sorry? Wales theorem, but it was not the equivalence between polytopes and cones. It said for polytopes can be described by cone plus convex or bunch of inequalities. What about cone? How do you describe a cone? Equations, give me equation. Let me remind you of something which is equivalent of Gaussian elimination. No, you are thinking of again mathematical, cone-wise, geometry-wise. Fourier-Motzkin, remember we got stuck multiple. Why did we do Fourier-Motzkin?
To solve for inequalities.
Right, so what kind of inequalities did we get? A cone is, okay, so you are probably confused with all this thing, but Wales theorem tells you that a finitely generated cone, a convex cone, is equivalent to a set which is it was a bunch of inequalities where B was all 0. This is what we did for Fourier-Motzkin, right? So again, all these things, I am not saying you should remember them, but yeah, Ax less than equal to B can really be, that be an inequality satisfying a cone? No, because I can multiply x by any constant, right? So for the cone, it is Ax less than equal to 0. So if given a quiz, right? So then these equivalences should flow, right? Given some time, you should be able to figure out, yeah, Ax less than equal to seems like a cone kind of an inequality. Ax less than equal to B seems more like a hyperplane, right? So this, great, right? So now that means my cone C also has this description, right? Every cone in the world has this description. So why not my favorite cone, cone C? That will also have that description, right? And now I know that B is not in cone C. What does that mean? Sorry? Okay. What does that mean? Again, I need a small a. Tell me what is the small a? Sorry? Capital A cannot be A. That A there is a vector. Capital A is a matrix, and that's the general notation we follow. Right? So clearly my small a is related to capital A. But how? What does this equation mean? This means first row of A multiplied by X is less than equal to 0. Second row of A multiplied by X is less than equal to 0. So if this is not satisfied, that means there exists a row of A such that so small a is that row of capital